In this video, we're going to take a look at finding more volumes, but we're going to use a different method. We're going to use something called the shell method, and I want to start us off with a motivating example. This is literally just an example that says, here's a good reason for why we might need another method of setting up an integral formula to find a volume. So let's take a look. Let's consider this region bounded by the graph y equals x squared minus x cubed. I've just factored this so we can see what this is going to look like, right? This is a negative facing cubic function with zeros at 0 and 1. No big deal. And we're looking at this in the first quadrant. We want to know what's the volume when we revolve around the y-axis. If we were going to do this using washers, we would draw a rectangle like this. And we'd revolve it around, and this seems great, right? Because we get this nice little washer here with some sort of a thickness. That thickness is going to be delta y, because that's the small direction of our rectangle. And we just need to be able to find, let me use my circle tool. I always forget. There we go. We just need to be able to find the area of this shape. Oh boy, this can't recognize that my circles are here. There we go. We need to find an area of this shape. We need a small radius, and we need a big radius. And this is when we start running into the problem, because our small radius is this distance, and our big radius is this distance. So both of these are x values, meaning we need to invert our function. So take this thing, solve for x. Good luck. And what you'll also notice is that this is not going to be an invertible function anyways. This function is not one-to-one. It doesn't pass the horizontal line test. Another way of saying this is that our washer has an inner and outer radius that are formed by the same function, right? It's still this x squared minus x cubed function. So even if we were able to do that, it would be the same function on both, and we'd end up having to subtract things weirdly, and things could get strange. Now, what you could do is something that we do in trig. You could say, well, that's no problem. Let's just cut it up right here, and we'll invert each of the pieces separately. So you'd have to slice things up maybe between these two blue lines, figure out what this function is and try and invert that, and then take the function after this second blue line and invert that, and you'd have different functions then, technically, that might be in different representations when you invert them, and hopefully we're going to notice that this is very hard. Washers are not going to work great here. So what we want to do is change the type of cross-sections that we look at. Instead of looking at these sliced up cross-sectional areas that are going to be looking like discs or washers, what we want to do is we want to take that region and we want to create little hollow cylinders, we'll call them shells, nested inside of each other. The way that we're going to do that is by, let me draw this region again, taking a look at this function, and instead of drawing our rectangles this way, what we're going to do is we're going to orient them this way. So now we have a little delta x here, which is going to be good because that means we don't have to invert anything, and we're going to revolve it around the y-axis. And the question is, well, what does that look like? They're going to be hollow cylinders. They're going to be shells. I've got a little animation that will hopefully help out with this. So let's take a look at this one. This is a different function, but here you can see they're splitting this up into a partition. They're going to take a look at rectangles on each of these. So here's one of the rectangles that's getting revolved around the y-axis. And you can see that once it comes all the way around, it's going to create a kind of sitting upright hollow cylinder. And what we need to do is figure out what the volume of each of these cylinders is going to be. So here it's going to take each of those rectangles, revolve it around slowly, halfway first, just so we can see a little bit about what these look like. And if we can find the volumes of each of these little cylinders and add them together, that's going to give a really nice approximation of the actual total thing. So here is our approximation. And I think in the next bit, we should be able to see the actual surface that they're going to generate when it's revolved around. So this is what the actual thing looks like when we spin it around the y-axis. But using those rectangles gives us a really nice approximation of it. And we know that once we take a look at the number of rectangles going to infinity, we'll be able to get an actual volume. So we're going to have to completely change our paradigm, figure out how to set these shells up, how to find the volumes of these. Let's get this going. Here we go, shell method. So I've just drawn a general picture. Again, it's just two functions. We've got an upper and a lower bound in this case, f and g, and I've got one rectangle between a and b, and I want to revolve that thing around. We now know a little bit about what that's going to look like. It's going to look like this skinny cylinder that we have. Something like this. And so we have to find the volume of this cylinder. Now, the volume of a cylinder is relatively easy. It's the area of the circle multiplied by the height, but that's not what we really mean, because that would include all of this inner part. And what we want to do is just find the volume held inside the walls of these cylinders. Notice this is delta x. That's this thickness of our wall. So we have to include this delta x in here and somehow come up with a way of defining this volume. The common thing that people want to do is to set this up as a cylinder inside of a cylinder and subtract the volumes like we did with the washers. The issue with that, though, is that the difference between the radii is delta x, and the problem there is that that's going to go to 0. And so we may end up getting a kind of nonsensical 0 volume. What we're going to do instead is we're going to slice this thing right down the middle, and we're going to open it up. So what this looks like then when we unroll it is a rectangle. You can think of taking like a toilet paper tube or paper towel roll or something like that and cutting that cardboard right up the middle, and what you end up with is this rectangle. And I'll add in a little thickness here. That would be like the thickness of the cardboard, which mostly is pretty small. So there's delta x. It's the thickness that we have. And now we're in this nice situation where we have a rectangle. Finding the area of this is not hard. It's length times height, or width times height, or whatever you want to call it. But the problem is that we're going to have to figure out what those things are. So let's start off with the height. The height, if we trace that back, that's, maybe I'll use blue actually for the height. The height, when we trace it back, is really the height of our cylinder. And that is the height of this rectangle. And we can see what that is. That's going to be f of x minus g of x. It's going to be the difference in the two y values. When we want to find the width, though, or the length, whatever you want to call it, that's actually going to be this distance around our cylinder. That is a circumference. So the circumference, if you remember, is pi times the diameter, or we might say pi times 2 times the radius, or 2 pi r. And so we need to figure out what the radius is. The radius is going to just be this length here up to whatever point we're using to define our heights. Notice that's from the inner portion to somewhere on the rectangle. That's right here. That's going to be an x value. Okay, so let's go ahead and do this. We'll do our slice and sum strategy. The volume of the kth slice is going to be the area of this rectangle at some x sub k star times delta x. Our area, we said, was going to be the circumference, 2 times pi times whatever x value we were looking at, x sub k star, times the height of our cylinder, f of x sub k star, minus g of x sub k star, times delta x. That is the volume of the general kth cylinder shell. Now, we can say the total volume of whatever region we're looking at is approximated by the sum of these. So 2 pi x sub k star times f of x sub k star minus g of x sub k star delta x. And then we can apply a limit. And this gets tedious to write after a while. Here we have this difference in heights again, times delta x. And the whole point is that this is going to turn into a limit. Our volume is going to be an integral. I'm going to factor out the 2 pi integral from a to b of x. Oh, I'm running out of room already. 2 pi integral from a to b of x times f of x minus g of x dx. And I probably have that on the next slide. There it is. So if f and g are continuous functions, where f is the bigger one, the taller one, greater than g of x on the interval from a to b, then the region bounded by the graphs f and g on that interval revolved around the y-axis is going to create some solid who has a volume, exactly what we just saw. And then we can say, well, what about when we revolve it around the x-axis? Notice this one is revolved around the y-axis, so when we revolve it around the x-axis, we're going to have to switch variables. So we'll say, all right, v is going to be 2 pi times the integral from c to d of y, f of y minus g of y dy. And again, we're not thinking about top and bottom, we're thinking about right and left because we're thinking about this inequality. Here, f of y has to be greater than or equal to g of y. So we're thinking about this one has bigger x values, it's further to the right. No big deal though, we just swap variables around. All right, so let's take a look at some old examples. This is one that we started off with. This was our motivating example. This would have been really annoying to do with washers. Hopefully, it's not that bad to do with shells. So I'll just give it a quick sketch. We've already seen what this looks like here, and we want to revolve around the y-axis. So now what I'm going to do is draw my rectangle as a tall, skinny rectangle with a delta y. When you revolve it around that axis, it's going to end up creating this little cylinder. When you cut this thing open, that's going to create a rectangle with a tiny thickness. That thickness is delta x. Oh, that looks like a y here. There we go, delta x. Maybe I did say delta y. I meant delta x. And then what we're going to need to know is the dimensions of these rectangles. The width of our rectangle, or the base of our rectangle, is the circumference of our cylinder, which we're going to need a radius for. This distance here is a horizontal distance. That's x. So that means our circumference is 2 pi x, and then the height of this thing is just x squared minus x cubed. It's that function value. So our volume ends up being 2 pi times the integral from 0 to 1 of x times x squared minus x cubed dx. Or we can say this is 2 pi times the integral from 0 to 1 of x cubed minus x to the 4. And then this should be easy to integrate. This is 2 pi times x to the 4 over 4 minus x to the 5 over 5. Evaluated from 0 to 1. So we have 2 pi times a fourth minus a fifth. A fourth minus a fifth is really 5 over 20 minus 4 over 20, so it's 1 over 20. So we have 2 pi times 1 over 20, or pi over 10. Cool. So this shell method, not too bad. Let's take a look at this old example. This is one that we looked at using some washers. This was one where we switched variables and we integrated with respect to y, but now we won't have to do that. So let's take a look at this square root function and this horizontal line at y equals 2. And now what we're going to do is, instead of drawing our washers going this way, or our discs, I guess, going this way, what we'll do is draw a little shell going this way. So we have a delta X here. So again, we're going to create this little cylinder. And that's going to, when we cut this open, turn into a rectangle. I'm going to use my straight line tool to draw that so it doesn't get so messy. Oops, there we go. So we've got this nice rectangle. That rectangle has a thickness of delta X because that's going to be the thickness of our walls of our cylinder. Then we need a width of our rectangle. That's going to be the circumference. We need a radius for that. The radius measuring from our axis of revolution to our rectangle is just the X value. So we have 2 pi X. And then the height is actually going to be our Y value of 2 minus our Y value of the square root of X. Because it's the difference in these things, right? Top horizontal line minus the bottom square root function. So our volume ends up being the integral from 0 to 4. Let me factor my 2 pi out front of X times 2 minus the square root of X dx. Notice we're not squaring our function here because we don't need to square anything in terms of radii squared. We're just multiplying by a height to find this area of our rectangle. So we've got 2 pi integral from 0 to 4 of 2x minus x to the 3/2 dx. And you could go out from here and finish this thing out. Go ahead and do that. Finish it out. Make sure that it does match up with what we found earlier. This should be the same volume as the way that we did it with discs. Here's another good motivating example. I think this is a really nice one to show off why the shell method can be helpful. So we're going to take a look at the first quadrant. We have a graph of x cubed, or x minus 1 cubed, sorry. That's a cubic function, shifted. And then we have this horizontal line, y equals 8. Oops. There we go. And we're looking at this region, and you can see hopefully the problem. The problem is that if we use, and we want to go around the x-axis, let me put that in as well. All right, so the problem is that if we use rectangles sitting up this way, we're going to have to split this into 2 regions. We're going to have to look at this spot here at 1, where our top function is 8 and our bottom function is 0. We can use discs here. Or, and then, sorry, we could go ahead and look at the second part where our top function is 8 and our bottom function is x minus 1 cubed. We'd have to use washers and combine these things together. Or what we can do is say, no, I don't want to do any of that. I'm going to use a cross section that looks like this. And now you'll notice we have the same rightmost function and leftmost function throughout the whole thing. Our cylinder now looks like this. When we rotate it or revolve it around the x-axis. And if we cut this thing open, we end up with something that looks like that. Now, hopefully, we can see we're going to have a delta y here, which means we're going to have a y value as our radius. So our circumference of this thing is really 2 pi y. And to find the width, we need an x value, and that's going to be this function inverted. So we've got the cube root of y equals x minus 1, or x equals the cube root of y plus 1. That's really what this green function is. So that is going to be our width. Our limits of integration are going to go from 0 up to this horizontal line at 8. And so our volume now is 2 pi times the integral from 0 to 8 of y times 1 plus the cube root of y dy. I think this is much easier to do with shells than it is to do as a combination of discs and washers. Again, I can let you figure the rest of this out. Let me just multiply, make this look nice. Y plus y to the 4/3 dy. And then you could go ahead and integrate from here. So I think that's a pretty good motivating example. All right, so the question is then, when do you use discs and washers versus shells? And really the answer is kind of it's up to you. It's almost like it's your choice, depending on your own preferences sometimes. In that first motivating example that we saw at the very beginning of this video, we realized that it was really, really difficult to switch variables because the function that we were looking at was not one-to-one, and so we couldn't find an inverse very easily. So what we should do is draw a region and maybe draw a horizontal rectangle and a vertical rectangle and try and see which one is going to be easiest. Is one of the rectangles touching the same function twice? That's going to be tricky. Are your functions one-to-one? Do you like switching variables? Would you rather not? What you'll notice is that with discs and washers, we use the same variable in the differential as the axis of revolution. What I mean by that is if you're using the x-axis, you're going to be integrating with regard to x, right? Because you have some sort of an axis here that you're revolving around. We set up our cross sections perpendicular to the axis. So our differential, our short side, the delta, is running the same way as our axis. Whereas with shells, we use the opposite variable in the differential as in the axis of revolution. And that's because, again, our cross sections, our little rectangles, are formed parallel to that axis of revolution. And so the small side, the delta variable side, is running perpendicular to the axis of revolution. So some of this is going to be dependent on whether you're able to or want to switch variables and what axis you're revolving around already. If you're revolving around the x-axis and you want to use discs and washers, you're going to anti-differentiate, with regard to x. When you're looking at shells and you're revolving around the x-axis, you're going to do it with regard to y. So just be careful about whether you can switch variables or not. Also take a look and see if you need to cut things up into multiple chunks, like in that first or second example, I think it was, where if we were going to use discs and washers, we'd have to use a combination of both, whereas with shells, we didn't have to do that. But really, part of the answer here is just practice and visualization. So jump into some problems, get some practice, draw some sketches, see if you can visualize, and let me know if you have any issues.